I think he went off on a trip to New Zealand or something like that.
Wrong side of the world, but close enough.
And I'm hoping he makes it back. I've had students before that had to turn things late because they were stuck in a foreign land. It's not a big deal. We usually just handle it. I turn it in when you get out of jail in Switzerland or whatever happened to you. Okay, so let's talk a little bit about OpenGL versioning first up. So OpenGL has versions just like any kind of software program. And just like any other kind of software program, the versions make varying amounts of sense, and sometimes it might resemble very little sense. But that's how they work. So we talked about this shift to 2 and the programmable shaders and how that was a pretty big paradigm shift. It wasn't until version 3 that a lot of the stuff from version 1 was actually deprecated. Stuff like GL Rotate and GL Translate and other old favorites from back in the game dev days. So all that stuff was actually deprecated in 3, and so it should be pretty well gone in 4, which is what the man pages are set up for on the system. So I thought it might be an interesting exercise to change to version 4.6. Unfortunately, 4.6 wasn't supported yet on the computer I tried it on, so I had to back off to 4.5. Anyway, it works in 4.6, or 4.5, excuse me, for the most part. It throws a couple of warnings that I don't think you actually have to fix, but it can be nice if you fix them. So not a lot of differences, really. It's like I said, it pretty much works. I'm going to go to, so I've got these the modern tutorials right here. I'm going to pull in a different set of the modern tutorials and put it in TMP. You can actually use Git to do this. I'm not going to, but you certainly can. Okay. Well, because that's where I have some things modified that I'm about to show you. Okay. So in these tutorials, inside there's this directory called common in here. We looked in it a while back. It's got the places that load the shader programs. So if you look at shaderutils.cpp, it's got a file read. I think we looked through that earlier. It's got other stuff, but eventually we get to this versioning thing. And so OpenGL for embedded systems is a different version. It's okay. Yeah, OpenGL or GLES version 2 isn't defined on our system, so we're fine. We're not worried about that. So this one, I think it says 120, which is OpenGL version 2 for reasons that I'm not completely aware of, but apparently they weren't very important because they changed the numbering here to match better later. So I updated that to version 450 and set it up to run for current OpenGL. Let's see how far off we are kind of exercise, you know? Figured that'd be fun. Okay, so what's that?
Were you gonna? I remember you usually shrink the screen so that people in the back have a slightly easier time seeing.
Oh, are you missing stuff on the camera because of it? Okay, I'll be more careful. I was thinking it with this wide, clear area with no heads that probably everybody in the back could see. Okay, so the version 450, we'll switch to that. Inside to see what happens. If you go to the cube here, or not cube, bush. I got to show you the rest of this thing in a minute. Okay, there's a couple of warnings here, none of which are very important. This thing's still called cube, and hey, it works. And it doesn't throw any warnings at all. But I did have to change a couple of things. Okay, cube.f.glsl. Let's start with the fragment shader. Okay, no, let's start with the vertex shader. Okay, so the vertex shader, there's a couple of things that might not be immediately recognizable. You see we got in and out vec3s there. And so if we look at the version that we had currently, here's what I'll do. I'll split my top frame. I don't know what fraction of the screen that even is, but we'll look at the original one. Okay. No, it's 205 cube. Okay. Okay. Oh, whoa. Well, it's got our win stuff in it. That's why it's long. Okay, so before we had, oh, this isn't even the same. Before we had attribute and uniform and varying. And so a couple of these have changed. Now they just say on the shader which direction they go. So if you have something that brings data into the shader, that's an in. If it brings it out, it's an out. If it goes in and out, it's an in out. I don't know if you're allowed to have those. But anyways, so you can change data in and out on that, and really it's not a big switch there. You just in some place have to say in instead of attribute and out instead of variant. Okay, so that was that one, the qualifier changes. That was actually kind of clear what happens anyway, to have in and out instead of attribute and varying. Attribute and varying were a little bit weird. I guess that's what everybody must have decided, right? So it must be, yeah.
If we want to take the game engine and throw it up to 4.5, what line do we have to add to make it start using 4.5?
Well, that line doesn't even exist in it right now because it doesn't have shaders.
So it has to be in the shader.
Yeah, that line was in the shader.
Okay, so in order to switch off of version 1, what do we have to do?
Read
we
the
have to
entire
do,
engine.
remove everything that's deprecated.
Okay.
So if it doesn't have a man page, it's got to go.
Yeah.
And that will require you to implement shaders. And once you've implemented shaders, they'll have a version tag at the beginning. And you set the version tag to 450.
So just the nature of implementing shaders automatically promotes your version.
Well, removing the deprecated stuff does.
Well, I mean, if you don't do that, it just won't work.
I think it will.
Oh. Well,
I haven't tried it, but I'm fairly certain that I could throw GL rotate into this Bush program and it would keep working.
So you can use deprecated stuff and shaders?
Probably.
Well, that doesn't seem right.
You can, but you probably shouldn't.
Okay, yeah, that's
So what's
really,
that good for?
yeah, you shouldn't. But I don't think it'll actually stop you probably. Now, you might end up with something funny, like suppose you say you got a version 450 shader, and say you decide to use a compute shader. Compute shaders weren't even available until version 4.3. So you got a compute shader in it, and you throw in a GL rotate, which was deprecated as a version 3. I suppose your video driver could say, error cannot load version 430 shader with version 1 point whatever calls included or something. But it would be your video driver that would say that. Like it would compile fine. Because you can compile, so for OpenGL, say take version 2. OpenGL version 2, you can write down the vertex shader and put it on the card, and you can call GL rotate app. And those are both perfectly legitimate in OpenGL version 2. So you can do both those things. But if you try and load a version 4 point something shader, maybe the driver will object.
Okay. Interesting.
Yeah. And the funny thing is, I ran into an objection with my version 450 shader where the video driver refused to load it. I went home and I loaded it on my old 9800 GT, which is going to be close to current again if they make another 9000 series. But I think it'll be like a 9080 instead of a 9800, so it won't quite match. Anyway, so the 9800, it doesn't work with the latest drivers. I have version 340 running on it, which is the legacy package. And the driver told me, we can't do this. We can't load a version 450 shader. So I backed off to version 400 and it said version 400 isn't fully supported, but we're going to load it and use it anyway. So if you're writing a game and you want to support legacy drivers, you have to be prepared. It might be that when you say to load the program, you get back an error that no, you can't do it with this version, and then you got to have another shader ready and be like, okay, fine, we'll use this shader instead.
So you mentioned that GL display lists changed.
Well, display lists are deprecated in the later versions.
So you have to use their modern version
You got to put everything into a buffer like this.
and then tell it to put that buffer on the graphics card.
Yeah.
for the shader.
Well, you just tell it that you're going to use the buffer to draw things, and hopefully it decides it goes on the graphics card.
Oh. So you tell it to make a display list, it will, but it just won't let you use shaders with a display list?
I don't think it will, because that's a 1 point whatever kind of call. The display list. The display list is the old way to get it on the card.
Yeah, but you can still use old ways.
Up to version 3, you can mix and match as you'd like.
Okay.
After version 3, it'll compile, but your card may object.
So if you did use a display list on version 3, could you use a shader on that display list?
I don't know how the interaction works. I don't think it's really very recommended.
Okay.
But I'm sure there's some way to do it.
Did you Jesse over there trying to figure out all the different ways you can break it.
Oh, it's just good to know all the various combinations. You know, you got to know what options you have. You know, the first thing you do when you get like a tool set at Christmas or something, you know, you're busy trying to see, you know, is there some way I can attach like the 1/4-inch socket to the big 1/2-inch wrench with a combination of adapters and thingies? You know you shouldn't, but you still want to know if you can.
Just in case you can't find that little one.
Yeah, you know, or there's like some bolts way back there, and you need like the 1/2-inch breaker bar to reach it. You know, there's going to be a reason sometime. Maybe.
I'm just trying to figure
I've
out.
actually been in situations where that exact thing happened.
Yeah.
I'm just trying to figure out how to do procedurally generated armor models.
Oh, the other thing you can do, so we haven't got there yet, but we will. There's 2 mechanisms for it. First of all, the compute shader. The compute shader is designed to have you have some sort of buffer, and you go run something on it in a shader, and then it goes back into the buffer so you can modify it. Oh, and then there's another thing you might want to use. Another thing you can use is the vertex shaders have a feedback option. So you can have some buffer and have another buffer, and you read one into the graphics, into the shader, and then besides drawing the output, you write it back into the other buffer so you have it again. I'm working on a demo to do that. I couldn't find it in any of these tutorials, and the only demo I found for it was 1,200 lines. So I want to make a simple one for us. And then finally, you use a geometry shader. So the geometry shader, you get all your terms passed into the shader. So if you got like armor, suppose. So you're going to take this armor and you're going to make a more better armor. You know, it's like this is a square, but we're going to make it the special armored square. When it comes into the geometry shader gets to say what primitives actually make up the final piece of armor.
Well, I'm just trying to figure out, like, I want shoulder spikes to grow the higher your defense stat gets.
Yeah, geometry shader can totally do that.
But it's just moving 2 vertices.
Oh, you can do that with a vertex shader too then.
But wouldn't you not want to waste a cycle on doing that?
Yeah, the fastest way on that is probably just to, well, maybe it's not, because you'd have to, if you got a whole big buffer with all this stuff, you'd have to bring it back to the CPU and put it back on the GPU. When you're going through the vertex shader anyway though, you can probably tag those 2 somehow and grow them. You can figure out where they are. And I realize this means that 2 of your shaders are doing, like hitting a true on an if and all the rest are hitting a false or something.
Now, theoretically, I can process everyone's armor all at once.
Yeah, certainly, there's a few options for it, I guess. So the in-out changes, and I think that's the only thing that's different in this one. Now, the other problem though, so you saw that the program worked because I ran it for you. In the fragment shader, there's been some different deprecation. It used to be in the fragment shader. Here's the fragment shader for the last time's demo, q.f.dlsl. So we have this thing, GL frag color. And we don't say what GL frag color is, but it's global in scope, and you set it, and it's the color for your fragment. And that's what happens afterwards. That's where the color for your fragment is. So this was deprecated in favor of something I've been kind of referring to as insanity. So this is a fragment shader program. And it's got 2 out vec4s. It's got gerbolator and rabidator. And so it sets them both to colors. And so they're different colors here. And let's go ahead and pull this thing out. And so if we run this thing, push, shrub, cube. You can see that they are in fact green. So since they're green, you can see that the one that we've picked is, it's actually coming through this one. This one is red here, Rabidator. And so Rabidator is not the color that we have chosen to make the fragments. In fact, Gerbolator is. Let's switch which one we use. Okay, take Gerbolator and put it down there. Now let's rerun the program. Now it is red. So, it's just a rule to remember. You guys are good at remembering little funny rules, right? Here's the second version, cube.f.dlsl. Okay, the one that you declare, the first out vec4 that you declare, whatever it happens to be called, is the frag color. And the second one you make doesn't do anything. So now you know. You're free to like or dislike it as you please. If you like the old system, just declare an out vec4 called GL frag color before you declare any other things that are out, and it'll work just like it did in the old days. Okay, so that's the other difference. Now, as you can see, these aren't really major paradigm shift kinds of things. And so if you want to take some code that was fully OpenGL 2.0 and move it up to OpenGL 4.5, there's very little to do. You have to change attribute and varying, and you might have to declare GL fried color, and there's other minor little details that may pop up, but they're really not that big a deal. So that's kind of cool. There are some additions. Bitwise operators are apparently supported in GLSL nowadays. They didn't used to be, but they are now. So you can ignore the whole thing I said a couple weeks ago about they're not supported because that's changed some years back.
Don't you love it when you find out about changes halfway through teaching something?
Oh yeah, yeah. No, this happens to me with C and C++ all the time. I'll be teaching something, I'm like, oh yeah, C can't do this. And then somebody's like, but what about the C++, 2020 standard that's supported in beta now in the latest GCC? And I'm like, oh, is it? Isn't that interesting now? C and C++ in particular tend to have the all-star set of features that people liked from other languages added to them. It's one of the great strengths of the language. C++ has got just about any feature you could want added in at some point. The disadvantage of C++ is it has just about any feature you could possibly want added into it at some point. And so it means that you could have two C++ programmers sitting next to each other writing C++ programs that really use a fairly small common feature set. Anyway, so there's that. And it also makes it very hard to master C++ in particular, because you have to know everything from C memory allocation all the way up through smart pointers. Otherwise, somebody can write a C++ program you don't understand.
Don't forget you can overload the new operator and stuff like that.
Yep, all overloading. And use of auto.
Yeah, you can do custom allocator.
And you have to learn macros. I was showing people the thing with the macros and making things that look like functions but are actually macros the other day in operating systems. And I realized all of a sudden, if you have operator overloading, you can actually make a function that in a Python way takes whatever types you want. It's not really a function, but it looks like a function.
Close enough.
If you make it lowercase, nobody's the wiser. And that's the other thing about the C++ family. There's a whole bunch of conventions that can be respected or disrespected.
And then there's ellipses.
Yeah. Oh yeah. So anyway, there's those changes, and that's that. So other things have come in now over the years. I talked about different fragment shapes, shader types, including up to compute shaders, which we'll use all of them. I'll tour the shaders at some point. Okay, so that's that. Let's talk about the generation and tree generation and that kind of stuff. Well, you can see it works. This is the thing I was going to talk about last time with the tree that's generated and waves in the breeze, and there it is spinning around and waving in the breeze. Okay.
And it was much, much wider in one dimension than the other.
It's actually wider on a diagonal on the dimensions, oddly enough. So the shrub maker and the shrub making. Last time I griped slightly about C versus C++ nested functions and lambdas, and mentioned that I'd been having trouble making a recursive lambda function. I figured out how to make recursive lambda functions, but by then I'd already just taken this out of the C file. So this is C, and it's got an indentation bug. There we go. Now it doesn't. So the indentation, so this shrub maker thing makes a struct shrub. So here's the funny thing about C and return values. Back in the old days, you'd return something that was register sized, and by old days, I mean old days, like 70s or something, back when my truck was made. Now, the more C from the fuel injection era didn't follow that convention anymore. You got a program that was written when people were running around with fuel injection, and you can return a struct. So a struct can vary in size. So let's look at a struct shrub real quick. I got a header here to unify the whole thing. Maybe no, I need to cube that H. Okay, so As of the Reagan administration, this is the thing you can return from a C function. I'm teaching history by putting parallel things together here. When, now you know what President Reagan and fuel injection have in common. They came about around the same time you can return a struct in C. Okay, so this is a struct shrub. It takes a size T and a float star, so it is a 2 8-byte value, so it's a 16-byte structure. And this float star is expected to be instantiated with some kind of memory, and indeed it is. Okay, so then there's a thing down here, which is commented out and spelled wrong. There it is. I'll show you where that came out. It came in later. Okay, so inside the shrub maker, what we're making is a struct shrub that represents a shrub. We go ahead and declare a struct shrub. This is allocated on the stack, but of course we're just going to return a copy of it, no big deal. We start out the number of vertices we have there at 0, and then we calculate the maximum size that we're likely to have based on the height of the tree. And so this particular tree doesn't have any branches that die off early, which is somewhat unrealistic. Normally trees assume a kind of rounded on the top shape. There's an all the branches are different lengths, but there's some of them continue further and some of them don't. This one, all the branches continue to sit just as far as every other branch, and so that's why it looks a little bit the way it does. My trees generated by this method tend to look like we got hit by the sky lawnmower. Which is also called a helicopter. They came out of the 60s when people were putting punch cards into machines, continuing our history theme. Okay, so the maximum size here, we take 2 to the level plus 2 power and multiply that by 3 vertices per, or 3 terms per vertex, and then we have 2 vertices per line after that. So once we got the maximum size, we go ahead and print it out because that was actually a debugging thing. That was my actual error. I was computing the size wrong and making it too small. So once we've computed the error, we go ahead and allocate enough space using malloc. So this will actually have to be freed at some point later, which is not our job. We return a pointer to it, and sooner or later, sorry, my pocket was full of grass. It was irritating me. Just about talking. Yes, from the haloing. Oh, not from the sky lawnmower. No. So then this add vertex function is just a little helper. All it does is add a vertex under a list by appending to n, which is the number of things that are on the list, number of floats. And so then we have this SS recur. And that was the whole thing that was giving me fits converting this to C++ because it's a recursive function inside a different function. So it takes a start and a level. So the float star here is actually a reference to a coordinate. And so it's expected to be the address of an array of 3 items, as you can see by the way we pull out X, Y, and Z. This looks kind of inefficient in the way of pulling out X, Y, and Z and making a copy of each of the 3 things just because we don't feel like typing start bracket 0 a bunch of times. But the optimizer should know that. And so where we say X, it probably is just going to say start at position 0. If we wanted to be really explicit about this, we could use pound define and done this macro style and had, X means start at position 0. Would work fine, but that's not what we did. Okay, so we've got these new positions, and that's where everything is going to end up at the end. We do some arithmetic here. Basically, Y is special. Y is a bigger increase than the X and Z dimensions. And we have one go positive on X and Z and one go negative on X and Z. And that's why it looks a little bit flattened. It's growing more along the diagonal between X and Z than it is off towards the center on either side. It wouldn't take that much finagling to fix it. The problem that you have on here is that the inside of the tree is too dense from branches re-entering and going into the inside. In real trees, this is discouraged because of shade issues. When a real tree is growing extra internal branches, they're shaded by other branches, and they're not found to be as productive. If you're managing an orchard, you actually cut those off, since you can just, we don't need to wait for the tree to decide that this one's too shaded. You just lop it off and that'll be good. But our tree doesn't have any pruning mechanism like that. It probably should. There's a lot of stuff here that could be done to make these trees look more realistic. But this is just kind of a quick algorithm to take two branches and bring them up in kind of random spots and random heights, and that ends up looking okay. So we have the vertex, and then okay, so we have to, the file format is a little bit inefficient here. The reason is we're actually storing each vertex about 3 times because we have this as a collection of lines, and so a line has 2 ends. And so if you got a line, and that came from a line, you end up storing this end of the line 3 times. There's probably a way to make this using GL line loop or something like that and optimize this to some extent. But it's going to be a lot more complicated than where you lay out the vertices because at the end of the branch, of course, you don't want to line loop back. I guess you could line loop. Well, then you got 2 lines that are in the same spot. It'll get complicated, you see. So that's why it's like this. Okay, so then if we got anything left on level, we go ahead and recurve, and we take one off our level, and that's the, this is the start point right there. It's wherever we said in its vertices plus however many is on there, -3, and that gives us this vertex right here, the one we just added onto the end. So we're passing the address of that on as the new start point, and then adding the level. Okay, so there's a recursive algorithm here, and in order to start it, we actually have to have a start point, just nature of the way the function works, sort of silly in a way, and then that goes off there and starts, and it returns our tree. Okay, it's not a big deal. Generate a tree. I actually do that in CS 111 as well, but I think they probably understand less well, and of course we do it in Python, so I don't spend any time at all talking about memory or structure, that sort of stuff. Okay, get these things together. So this file just has this in here, and it includes cube.h. The other one, I should really rename this because it doesn't display a cube anymore, has this line up here, extern C struct shrub maker float 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 in. So that's saying that we're going to have a C function, and it's extern in the sense that it's not declared in this file, which it can't be because this is a C++ file. It'll run into a compiler error from the nested function if we were to put it there. And so the compiler should expect to find a C function somewhere from that. So you'll compile it together and the compiler's happy. So if you want to mix C and C++ ever for any reason, this is the extent of the painfulness. It's really not that bad at all. The only thing that's bad is remember what you can and can't do in each of your files. Okay, so let me go ahead and pull in cube.h so we know what a struct shrub looks like, and we make a struct shrub. And so then we make it. I think that stands for bush shrub or something like that. I don't remember. We start the shrub maker there. We make our new bush shrub, and then it's finished it. And print out a few random little addresses and stuff, and on we go.
Yes. Bush shrub. That's what it means.
Yeah, yeah. So then we make these shrubs and whatnot with our shrub maker. Okay, so cool. We got a shrub maker. Shrub maker works. Okay, as far as how the data works on this, so our shrub here has a malloc heap allocated area memory, and so it works exactly the same way as it did before when it was on the stack. You see with the cube went somewhere like this. It's stack allocated memory. It doesn't even make a difference on here. All you have to do is you see so what you have. We have an array buffer, and it's got this many floats. bs.n keeps track of how many we actually have. And there's where they're located. That's the memory address. bs.vertices, the heap address. And in GL static draw, so remember that's how we intend to use the buffer. So Jesse was talking about display lists earlier, and I didn't clarify for everybody that hasn't been using those in OpenGL 1 point whatever. These are an archaic mechanism to store things on a GPU. The way a display list works, you say, okay, we're starting a new list. Remember this. Then you put whatever OpenGL commands you intend to repeat regularly, and then you just say, okay, done with the list. And you have a number for the list. It's like list number 1 or number 2 or whatever. So then it can squirrel away whatever it needs for these commands on the video card, and then when you're going to draw a frame, you just say, okay, run list 1. And sorry, then it can do that. I don't think that's from the hay, because I'm not allergic to it. Okay, the guy that helped me load was. He was taking Benadryl by the end. Okay, yeah, but he was getting my money at the end, not the other way around. He can pay for his Benadryl. Okay. So we just say static draw on its buffer, and off it goes to the card, almost certainly, especially on these machines where there's plenty of space on the card. Part of the reason that it's not really fixed, like we're not saying, okay, it goes on the card, is we're giving the video driver some flexibility. I am drawing a blank on how much video memory we have.
I think it's 6 or.
Okay, here's the video settings, and so if we, maybe it's right on there, nope, maybe it's right here. Okay, so there's information on the card, and it has, yeah, 4,096 megabytes total memory. How much are we using right now? 107. So that's how much we're apparently using to draw our two-dimensional, non-accelerated user interface, apparently. But the fact is, a lot of times when you have the memory, there's something that it can be used for, but it's not really needed. Like, sure, rat poison here would run just fine with like a megabyte of video memory. It'd be fine. But since we got 4 gigabytes sitting around, you know, I can think of something to cache there or something like that. But anyway, that's how much we've got, 4,000 megabytes. So on a computer, though, we've got 4,000 megabytes, 4 gigabytes. On a computer, we've got 128 gigabytes. So that means we could load something up. Where's that thing that we were just talking about? There, this thing. So we could pass this a pointer to, say, a 16 gigabyte array. And this could be the pointer to it. This could just be, you know, 16 gigabytes. And we could say, hey, this is a static draw array. We're going to draw this 16 gigabytes worth of vertex data in a minute. If we said that, the video driver would have to keep it in CPU memory. We wouldn't have a choice. And the video card can probably do that. I'm sure it's supported. We're going to have a lousy frame rate because it's going to have to pull 16 gigabytes through the PCI Express bus every frame. But it can do it. And so this is what happens a lot of times. You take a really old video card and you load a modern game on it with large models. Even if the game loads, you might be looking at like 3 frames per second. And that could be why. The other reason it could be why is perhaps your card just doesn't have enough vertex shaders to knock out the whole scene very quickly. Combination of things. But you'll probably be inspired to either turn the resolution down, which eases up the load, particularly on stuff like fragment shaders, or you can tell it, okay, instead of using like the models that look nice, we're going to use models that look lousy because at least we'll have a frame rate then. Most games support that. And then most games support other things. You can say, okay, instead of, you know, like 8 times anti-aliasing, we're just going to turn anti-aliasing off. No anti-aliasing. I don't care what it looks like. I just want to see it move. Most of the games, if you're like, okay, this game just came out, and I'm going to load it up on my old 9800 GT, you just say, I don't care what it looks like, just make it move, and it'll work. The quality settings usually go down far enough. One trick, if you're actually doing it, suppose you have like a 4K monitor, and you've somehow managed to plug it into your 9800 GT, which you can actually do. I've done that. Then it's going to look great in 2D, and that's why. It's not going to work very well in 3D. If you reduce the resolution to exactly 1/2 in each of the dimensions of your monitor, it'll look better than if you do it some other fraction. Since then you're just taking your 4K monitor and you're grouping the pixels together in 4s. People from the older days, the CRT generation, we always grumble a little bit when we do it. Because if you take your CRT monitor and you're like, you know, my game is not running the 1600, 1200, okay, let's turn it down to 1024, 768. You didn't have to worry about the pixel size. They would draw the pixels exactly the right size. Because it just had a phosphor screen on the front. And the phosphor did have a dot size, but it was really tiny. And so it would draw you actual pixels of whatever grid size you like. You can even have a different aspect ratio drawn on it if you like. You can do it. Okay.
Looks funny sometimes, but
yeah, but you wouldn't have any trouble from the fixed pixels. We're going that way on the LCDs. With the 4K and then moving to 8K, it's getting to the point where the pixels are starting to be small enough it's hard for people to perceive the difference. And so we got a long ways to go. But once we get down to phosphor dot size, people aren't going to be able to see the pixels anyway. Oh, there we go. Okay, so there's that call there, and that's what we're doing, and GL static draw and whatnot. Okay, so once all that stuff's in, everything else is just pretty well exactly the same way it was in the wind demo yesterday. I think we're completely out of things that are different. And so yeah, it does its thing there, and everything's great. So we want to turn that back so it's a green tree again instead of a red tree. I realize a red tree has maybe been more appropriate this fire season. Okay, we move Rabbitator and declare that second, declare Gerbolator first. As you remember, that fixes it, and now it's a green tree. And so in the virtual world, this is all we need to do to turn all the brush green and stop fire season. Okay, so let's make there be, all right, I had a couple of things I wanted to do. Yeah, let's do the first one. Let's do the forest one. And so we're going to add a second tree. We'll do the second tree first. Okay, if you want more than one tree and you don't want to clog up your GPU memory with a whole bunch of trees, you just got to draw the second tree in a different spot. Piece of cake. Okay, we take our cube thing. The spot that is drawn in has to do with this stuff up here and these matrices. We went through these things last time, and I think we actually even moved it around. If you look at the model matrix right here, it's got this GLM translate, and the GLM translate moves things around, and this one moves it -4 down the z-axis. So if you want our tree to be like really far away, you can say -40. And we got to make it for that change. And I think it's beyond the clip plane. I'm not sure what the clip plane is set to. Oh, the clip plane is set to 10. Let's set it to 100. Now we can see further. There we go. Little tiny tree off in the distance. Cool. Okay, so that's what our translate there does. So in terms of where we want our second tree, maybe just take 1 on the x-axis. This should still be something we can see. And we just stick over a little bit. Okay, we want to draw 2 of them. Okay, so looking at this code here, this is the on idle function. So when nothing else is happening, or often it means being synced to the refresh rate on the monitor, we're going to do this set of stuff here. And at the end of it, GL post redisplay will have the effect of running the on display function right down here and making all that stuff happen. So up here, we're starting by getting the time there, and then we're making our matrices, and we're doing our wind calculation, saying we're going to use the program, and we're passing in our matrix there and our wind, and then we're calling GL post redisplay, which runs us right down here, and so then we're clearing everything, and we're using the program, and which we actually said we were doing up here too, so it might be redundant. Then we're enabling our vertex attribute array here for the 3D coordinates of this thing. And we're binding a buffer here. And we actually have to do this, chord 3D. I'm entirely certain we do. But eventually down here, we're saying that we're going to GL draw arrays. Draw the arrays we currently have loaded. So what we want to do is draw it twice. But between these, we want to change the matrix. Okay, and so there we run into a little bit of a problem, a scope problem, because the matrix is no longer in scope down here, it went down to scope right there. So we're going to actually move a bunch of this code. We'll take everything except the GL post display out of the on idle, and we'll put it in the on display. This is actually not a very huge change because all that stuff was happening first anyway, most of the frames we were drawing. And so it's going to do the same thing. The only real difference is the on display now does these other calculations and grabs our matrices and sets them up and whatnot, which is fine. It can do that. It just means that if we do a resize window, all the stuff that probably should happen anyway is going to happen. Okay, but now these matrices are in scope. So let's take our matrix calculation down below. And we'll bring it down there, and then we'll gut it down there. So this is like when you take a feral camel in Australia and you bring it home in one piece, and then you take out the pieces you actually need. They actually sell camel meat at very competitive prices for camels because the outback is overrun with camels that are quite an invasive species there. Well, okay, this way when at the review time, nobody could say that Daniel never learned anything in this class. Okay, so the we're taking this. Okay, so this line here is important since we need to translate to a different position for the new tree. Let's say we just want to go 1 down the x-axis. The anim is not important, and we tend to leave that matrix alone. The view is not important, we're leaving that one alone. Projection matrix is not important, we're leaving that one alone. We're going to have to recalculate this general matrix, MVP. The wind doesn't need recalculated. This doesn't need to be redefined. That line, empty line can go away. Then we have use program, and we're setting these 2 things here. We'll have to reset our MVP before we draw things. So that has to be there. That use program is sort of redundant. That would be like the 3rd repeat of that line. So we do have to send that one out there. The wind is already there, and it's already fine. And then finally, we want to GL draw arrays again after we've changed where we're drawing things at. Okay. Then we're going to have a couple of issues here with these things that are redeclared. They don't need to be redeclared, they just need to be changed. And at that point, we should have, so we draw the old tree up here, then we recalculate the model view with the tree in a different spot, recalculate our combined matrix that has our model and view and projection and anim and everything in it. And then we reload that on the video card, give it a new copy of it, and then we'll draw again. Draw 3 again. Let's see what happens. There we go. Maybe that was a little close. There's sort of a stack there, it's like flat panels. You can see when they come by. There's almost a little tiny gap between them because they're so flat. But you can see they're in the breeze together. So if we wanted to loop this thing,
because rather than having the whole scene rotating, the trees themselves are rotating individually.
Right, they are. This is trees that have been planted in flower pots on a carousel. Okay, so I just put this in a loop to repeat it 10 times. I is where these things are going. And so if we say 1.0 plus I, then it should plant them in a row. There we go. Now they're all individually spinning. So I guess they're all, this is like a
That's why I was like,
a tree waving scene. That's what this is. Okay. They're kind of off the side of the screen. If we say this, say we start this at like a negative 5.0 plus I, except that we want to skip when I is 0, because that would be just in exactly the same spot as the original. Well, no, it's not when that is. It's when negative 5 plus I is 0. Minus 5.0, or 5 plus I is 0. Then continue. So just skip that one. This is already got drawn. We could just comment it out up here and not actually draw it up here. That would be fine too. Oh, we got a thing going on here. We don't need those both.
I was wondering.
Well, I think he meant to put those stuff you dragged down in between those 2.
Yeah, I wrote that earlier, and then you're right. I put all that stuff down there, and so I was actually drawing an extra tree that was on top of the other tree. Anyway, there we go. There's our trees.
Add a random in there so they're not all identical.
Well, we could make another tree model. But remember, this is the tree model that we have in GPU memory.
It's
So
just reusing the pre-existing model.
You do the whole billboarding thing,
the what thing?
where you take 2 of them and you like line them up so that.
Oh yeah,
So, like,
yeah, you could. You could totally do that.
Drawn in the same space, but with a
Yeah.
90-degree rotation.
yeah, I just remember that from game design when we spent like an entire day talking about all the instances that we saw that in.
Yeah.
Yeah.
Okay. I'm gonna take this one out because it's weird, and I'm gonna take that out because it's weird, and separate them by a little bit more. And so then down here, we did our model view and whatnot right there. So we need to include a rotation. Before we have a rotate in this animation up there, said GLM rotate, we took that and rotated it. But let's grab this line here and just bring it down here. And I've got an idea how to do this. Okay, so we're gonna have to change our matrix, and instead of the anim matrix, we'll put this back in the model matrix, and we'll recalculate the MVP after that. And then, so we want to GLM rotate. We're going to start with the old model matrix, like that, and we'll rotate it by its angle there on the y-axis, which is already calculated. So then after that, we got to reload it to the card and redraw everything. So that's the second one. Now, there might be an order of operations bug here. We'll see.
This might cause some interesting weird things to happen.
No, I think it worked.
Except you just
Now, the wind is a little bit funny. I'm not sure quite how the wind is. Some of them are rotating faster than
half of them,
others.
the new ones are rotating at twice the speed, and the other ones
That's what it is.
Yeah, that was a little odd.
because you doubled the amount of rotation on the secondary trees.
I said angle here. I shouldn't have said angle. I should have said 90.
Yeah.
There we go. Now we
That's
got
much
it.
better.
Yeah, our,
It's still weird looking, but
well,
It's not natural.
the wind is applied after the model view, so the two sides of the tree are
Are
shifting in the
independent.
wind a little bit differently. We'd have to change how we do the wind a little bit to fix that. The wind is done in here. See, there's a wind calculation up there on the Z disk. So GL position is all of this stuff with the MPV multiplied by it. I think what we'd have to do this second after I don't know if we can modify GL position. I might not like that very much. We can make an intermediate one here. If we said that this is going to be it's just going to be vector vec4. Call it. I can't call it int. I'll just call it I. Okay, so this is we're gonna have to decompose these. Let's say I dot x here. This is gonna be I dot z, and might as well have a. Y. Let's call them y, x, y, z. Actually, let's use I dot x, y, z. Why not? I'm being weird here. Okay. So if this is greater than -2, we want to change x by adding on something related to the y coordinate plus 2 divided by 5 times the wind. And at the end of this, GL position, think out what comes out of this, equals I. Okay, this has got to be I dot x. Okay. Undefined variable z disk.
And the X disk.
Oh, there.
Vec4.
I think we just say Chord 3D here because we're not using any of that stuff anymore. There we go.
There we go.
More
That's-
Oh wow, that looks a lot better.
Oh, yeah.
Yeah, it's also, we sort of changed the way the wind happens too. Instead of us, so the wind's coming from a consistent direction now.
Yeah,
The wind is going towards the left. The trees are still rotating independently because they're each growing out of a flower pot, mounted on its own independent carousel, and they're all synchronized. So imagine it, the carousels, the flower pots are mounted on a like a microwave spinning tray, a turntable, except that they've got like a gear on them and they've got a common chain uniting them in the same speed or something like that. This could be made out of like old bicycle parts or something like that. I'm sure we could rig this up.
And all of these plots are somehow identical.
Well, the trees are identical.
All the
throughout.
trees that grew out of the pots are identical.
Yeah.
Yeah.
So let's use shaders to generate dynamic trees.
That's not that hard to get identical trees. They have like special little plastic things you can put over the shrubs to make them grow in certain ways.
Or you could use a plastic shrub.
This doesn't say.
I thought we were talking about real plants though. So, nah, I'm talking about real things.
Well, seeing a real power plant is hard to model. We could just say this is a plastic plant.
It makes its own wind, apparently.
It's a plastic aquarium plant. This is a current from your pump.
There you go.
Okay, so that does make these things spin and whatnot. So, okay, so we got the vertex shooter there, we got the wind going, and we've got a bunch of these plants, and that's kind of cool. And so we got our little scene there. Cool. Okay. I don't know what's being printed out at that point. Okay. Okay, so now that that's set, so far we haven't been able to move or go places at all. And so that's kind of a weakness in these sorts of things. So I want to kind of set that up real quick. I'm concerned that I'm turning cube into too elaborate a test bed, but I think it's adequately hacked together and junky enough that we will actually abandon it next week. I'm hoping. See, this is Fred Brooks, Mythical Man Month. I used to have this as a book that people would read for CS 101 some years back. I have been requiring a different book as of late. But anyway, he talks about how you got to plan to throw one away. And it's always tempting to just keep the prototype and use it and release it, but it's a bad idea. You just need to force yourself to throw away the first one. And it really is good advice. Okay, anyway, design controls. Controls just mean we have to know where we are. And it's good to know where you are anyway. So suppose that we're just going to walk around in the XY plane, and we just need an X and Y location. Hey, where are we? If we look at the matrix setup here, we've got a view here where we've got a GLU look at, and that actually has encoded in it where exactly we are. I just said GLU look at by accident. These GLM functions are structured after the OpenGL 1 point whatever constructs that are named the same thing. So if you're curious what GLM : look at does, you can actually look up GLU look at, and it does the same thing. The way the parameters work and whatnot. So we try that. GLU look at. GLU look at is documented by the Carlos group here, and it's got these 9 parameters. And the I, X, Y, and Z is just where your I is. Incidentally, you only have one I in 3 dimensions. Just remember that.
And most of the time, when you're using a model, they put the eye right here.
Yeah. Everybody is actually a Cyclops. Okay. So let's have our position. So we'll make that a float, and we'll call this PX, PY, PZ. That's where we are. And we can give ourselves some initial values on here. 0, 0, and where are we normally? Let's just go where we normally are to start. That'll be a good spot. So we're at normal, and then 2 on the z-axis. Okay. Equals 0, dy. We can actually use a vec3 here. Okay, so there we are. That's going to be our position. Down here, all we have to do is put that into our position. And so there we are. Px, py, pz. Okay, we don't really have a good way to change that at the moment. So let's just add one. Let's say we're getting further away. So every time we display this thing, we'll say pz plus equals 0.1. So we'll just move a little tiny bit. It's actually going to move us backwards.
Yeah, so that's pretty quick actually.
There we go. Goodbye, trees. But see, normally in a movie, when you zoom out like that, suppose you're like watching this orc, and then you zoom out. You expect to see like hundreds of orcs, right? You'd be disappointed if, it's like this big battle scene, and you look at these close-up of orcs, and then it zooms out, and there's like 4. This is easy fix. These are computers. These things are automated. We'll start I out at -50, and we'll run I until positive 50.
Positive 500.
We could. This computer can handle it. This one has a 970. The rest of them have 1070s. My 4 GB number might be wrong in the rest of them.
Yep.
Anyway,
Oh, hey, look.
yeah.
We found the edge of the forest.
It's not a forest, it's a line of trees.
This is true.
You're right, it is not a grid. We could make it a grid. If you prefer a grid, grids are easy. We probably should, because I said in my notes we're going to for us.
Make a grid with
Can you do a diagonal for this?
You could do a lot of things.
Yeah, they could be diagonal.
Yeah, let's do that, so actually let's support.
Or you can
Just like
make
run them on a
diamond shape.
diagonal, okay.
Diamond shape? No.
I see what you mean. You still want a grid though, okay.
Yeah, grid, make the grid, but then turn it to the side, like 90 degrees, and then you actually get the perspective of the trees. So,
Yeah,
Or you can
so they're like offset, okay.
where the trees.
You know, the easiest thing to do here is actually change our perspective and just back off at a diagonal instead of looking at the center.
that works too.
Okay,
So what they're different axes.
Get over there?
Yeah.
okay.
Slowly dying inside in the corner.
What are we all?
Okay, so before we had that in that direction, so now we're just going to the Z direction too. So to say J is probably fine actually. Okay, so we're backing
Whoa.
down the aisleway there. You can see that we're backing down the aisleway. And
There is
eventually
a lot of trees in this.
we will probably come to the back of the forest. There
There
it is.
we go.
Okay, but we were gonna back off at a diagonal instead. So backing up at a diagonal, we'll add to our Z position, or let's say Px plus equals 0.1. We'll back off at the same speed in the X direction. Let's see what we're actually looking at. Well, this should be fine. Let's just see what happens. Okay, you can see us
Oh,
back
whoa.
Returning.
It looks
A
like
little
it looks like we are going in an egg. We're going in a curve.
Circles.
It's kind
Well,
of
we were at first just because of where we were, and there you can see it. Now, any decent movie like this will start to increase your altitude a little bit too.
really small amounts.
Yeah, that's probably too much actually.
Yeah, I would have went with like 0.01. It would have
Oh,
looked
that
better.
could be. Why are they sweating out of sync?
I think you're right, 0.01.
Because then as we zoom away, it'll slowly lift up.
They look
It
green.
looks like a field.
Uh-huh.
Yeah, it's awesome.
It looks less like trees and more like tall grass. I love how it slows down, the tree movement slows down the further away we get.
Yeah, we're actually slowing up the 970 in here a little bit. Let's do something else too. So down here, where Alex can't see it, I'm going to pull up a secret display. And, so you see you probably nobody but Matt can see this. It says use dedicated memory 120 megabytes right down here. And let's go ahead and run our cube. Hey, look at it. Oh, is that it?
It's
138.
not that much.
That's really not. Now we're not letting it cull vertices you can't see. I mean, out there there's just like vertex soup that it's still having to adjust every single time, so we're not really using it very efficiently. And it might actually stay smoother on the computers around the room. We've only got 1,664 cores on this one. Around the room have 1,920, and they're a little higher frequency, and they probably got faster memory. And hey,
And the tree is gone.
Okay, so there's an artistic pull away.
From the plastic bushes that are doing pirouettes.
Yeah, if we wanted our pull away to be longer, we can actually start ourselves off at down near the corner. We started at this position right here, but if we started at like say -40 and -40, then we'd be down near the end of things, and so we'll get to go over the full amount of these bushes. Are we going forward?
We are totally going forward.
Oh, yeah, but we're going to turn around halfway through.
Oh, that's cool. Actually, that looked pretty cool. Actually,
Yeah, actually, that wasn't bad at all, actually.
Like an eagle-eye view.
Yeah, I kind of like that, actually.
Gotta love it when unintended things happen that look
Right.
cool.
The reason that happened, so our look at point is still in the center. We never moved our look at point the whole time, so we're still looking at the same point. It's ahead of us there, but then after we look at it, it gets behind us.
Fly by with a flying grass mower.
Yeah. If we change this so we miss it, instead of looking quite down so much, we'll look over to it a little bit more. If we were to say 30 on here, we'll actually kind of miss our point a little bit. So you can see we're going past this whole thing. Actually, the frame rate kind of improves when most of these things are on a screen. So there you see we look at it and spin around, and off we go. Okay. Right now these trees have a uniform color from top to bottom, which is maybe thrown off the appearance.
Make them
just a
brown,
little bit.
fade to green.
Yeah, that would actually make a lot of sense. So we're taking this InVet F color and we're just passing it on verbatim here in the fragment shader. So in the fragment shader, we're really letting the vertex shader handle the colors, which is okay. We're coloring it by vertex, and this is interpolating between them. But that does mean that over here in the vertex shader, we can change the color, which is handy because in the fragment shader, we don't know the 3D coordinates of the point that we're this fragment. We could pass it through if we really wanted to know. It wouldn't be that hard. But we can also just give it a different color that's related in some way to the y coordinate. So the y coordinate on the trees is actually from a pretty small range, the I dot y. And if we take I dot y and put it here, it's probably too big. So we could just make some float here, y color, or some kind of formula. So if we take I dot y, it might be, if it's, it could be, where the trees go, they go up a ways. We'll let it max out after a while. So let's first of all just look at what this looks like. We set it to 1.0, just in a color sense. We saw what it says, look at it, we set it to 0. That's the forest green that they currently are. Oh yeah, rebuild it. So that's kind of that color.
They're orange.
Yeah, it's fall. So supposing we start off with that one on the bottom. We could say, we'll take the I and we'll reverse it. So now I is going the opposite direction, I dot y. And so then we want to kind of constrain it. So if I dot y is, tell us float R for the red, green, blue. And so if minus I dot y is greater than, say, 2, then we'll go ahead and max it out. R equals 1.0 F. Replace all instances of 2 spaces with a tab everywhere. Okay, so LF, we have to say LC. So minus I dot y is less than 0. We'll go ahead and minimize it. Okay, and finally, that means we're between them somewhere. R equals I dot y divided by 2 minus I dot y. They're all minus I dot y. Okay.
Why do you have that extra I minus I dot y up there
It's not gonna like that.
above float R?
Without talking. Okay. So there we've got R set based on this thing, and I realize it's a convoluted way to say it, but these days our shaders are perfectly happy with complicated things.
That's neat.
Yeah, we might have
But
wanted
the higher
to-
we get up, the more red they turn.
Wait, are you raising that up on screen coordinates?
I think he's
Now,
basing
isn't
that
that interesting?
So,
Yeah, that's what's happening. So what we're doing here is we're letting all of our MVP translation happen first, and then we're basing this entire thing here on the post-transformation spots. Which, I mean, that looked interesting. I'll give it that. Interesting. So what we actually want to base it on is the chord 3D. So I'll go ahead and make a variable for you here.
Man, that expression you had was great.
Y. Okay. Let's call him Y. Okay, cool. Let's see what happens now. Okay, so the bottoms of them are yellow. We could have probably gone yellow a little higher. Because I'm not seeing that much yellow.
Does the stuff die from the top down though? Like, would it be brown on
It's
top?
supposed to be the brown is supposed to be the trunk of the tree.
Oh yeah, it's a tree. It's I keep thinking shrub. Yeah.
I know.
Sorry, because it looks like a shrub.
2. We do -2.
Shrubs.
It's a shrubbery.
All right, I'm just thinking how to do this. Since we're going to span this area with 0. So I want to say 4 there, but I want to say +2 here. This is a convoluted expression now. And I want to say -2 right there, I think. That's high.
That's a little bit more obvious.
So really, we ought to make this map like easier. This is ridiculously convoluted for what we're doing. It's almost like I was trying to make it weird and confusing, and I really wasn't. That's higher. Let's go higher still. Let's go 8. 8, 10. Okay. I don't remember how tall these trees actually are. Apparently they're pretty tall.
That's like halfway, just past.
Yeah, that's
Yeah.
not halfway up the tree. Pretty good.
Well, the trees. Yeah, you think that's pretty good? Or should we go 16? Let's see what it looks like.
It's not
On the same spot.
any different.
Am I understanding this logic wrong? If it's greater than 2. Okay, this whole thing is ridiculous. So,
I don't think it was moving.
I'm not sure it was either.
okay, so we want it to be lower as it's, more towards the ground. So if we take something up here, we say the R is equal to 0 minus chord 3D.y. So the bottom of the tree, though, we're using mixing in knowledge from our thing here now. But the bottom of the tree is at like -2, if I remember right. It has the shrub maker there, -2. So that's the bottom of the tree. So the height that things are on a tree is -2 minus chord 3D positive again. Could that be more convoluted?
Let's just make it more complicated. Yeah.
I think that's the same as this +2. That's the height. Okay, so once we've got the height in the tree, then we can craft a decent expression based on the height. So we can say R, the red value here, equals the height divided by something, like 10. Except we want the opposite of height, because we want it to get less red as it gets higher. So we really want like the negative of height, the opposite of height, divided by 10. And so that will actually, as height goes up, that will get smaller. So we want like 10 plus that. Okay, so that means that if height was 0, then this gives us 10. If height is 10, then this gives us 9. If height is 100, this gives us 0. See how that works? Okay. So then the main problem here is that R might be too high. So if R is greater than 1, then R equals 1. As well. Okay. So I need that nonsense. Okay. So that should take care of that. The divided by 10 might be too strong. It might be read too high up. But more complicated. Okay, 10 was too much. Let's go just like 1 for now. See what that is. That'll be it. Oh, no, it's something other thing. Whatever the maximum for height is. So we take minus 10 minus height divided by 0.5. Divided by 0.05. Okay, so I just gotta get this dialed in. 0.2. There's 2. So 3 should be a little higher still. There's 3.
That's way too high.
Yeah,
1.7.
the 2 is better. 1.7, you think?
2 is still a little too high, I think.
There we go.
That's pretty good.
I wish the transition were just a little more feathered.
Yeah. But now at least they look like semi-healthy trees.
Yeah. Reason it's not feathered. I just cut off like abruptly. Are we doing integer math? No. I don't think so anyway. Integer division? No. I just blow. I don't know why we're cutting it off. Why we're not transitioning it better. But it's a total like artistry thing at this point. Okay, so we've got our field of trees. We've got some motion. We didn't add controls to control a motion, but we've got a nice animation. Sort of like it. I do. Anyway.
The forest of dancing trees.
Add
Yeah.
fruit works.
What's that?
Add fruit.
Add fruit.
Put red spheres randomly throughout the trees.
Can be done. So to do fruit, we're not going to get fruit in 5 minutes. Fruit's more complicated than that. So if the fruit is solid, for example, we need to draw something with GL triangles. And so what we could do is have our fruit function, or our shrub maker function, return a set of vertices that form a tree, the branches, and return a set of vertices where each vertex ought to have a fruit. And then, so we have the vertex of a fruit, and we probably know what we want a fruit to be. We could use the vertex shader to take a fruit vertex and then draw the rest of the fruit based on it. Just one fruit vertex, you know, it makes a whole like sphere or something like that. And actually, that would be a really good teapot. Yeah, I like that one. That would be a pretty good demonstration of how a geometry shader works. Putting those together. So I actually kind of like that as an idea for a demo for Monday. I feel like now I should just make it like the surprise lab, but I was thinking about the lab thing, and I decided it was really not fair to just make a lab for the day we didn't have a lab anyway. So I didn't really do that. I thought about it later. Tempered my enthusiasm for it. Okay, so anyway, that's probably where we'll go next time is geometry shaders. Geometry shaders were one of the other candidates for today's talk. I had 3 candidates for today's talk. The first one was getting a little bit more in depth with how do you actually use these and do stuff with it and accomplish tasks, which is what I eventually went for, because I thought that going to geometry shaders might be just getting ahead of ourselves and doing what I was excited about instead of what was best for the class pace and whatnot. So we went to more depth on that kind of stuff. I wanted to talk about the versions because I tried that out on Wednesday and got excited about it. The other candidates were geometry shaders, where we're going to add stuff, which might be next time. Compute shaders, which I decided was definitely getting ahead of ourselves, or translation feedback. So you can have a vertex shader move your vertices like ours does, but then write that back into a buffer that you can use again. And in fact, you can go feed that buffer back into the vertex shader and actually move things. So I was going to have our tree like, you know, melt or fall apart or something like that.
Helpful, you're trying to keep your physics on the GPU.
Right. Yeah. And so we can actually have the vertex shader do our physics, which could be cool. But again, I thought that was getting ahead of ourselves. But all of these topics will probably come up sometime soon. You can also use a compute shader for that kind of thing. If you want to have like particle effects for your tree, you can do them in a compute shader. But compute shaders were supported in LCSC 4.3. And so a lot of the particle effect demos are actually using the vertex shader and feedback or that kind of thing. Hacking a geometry shader in some way to do it. And people were hacking these shaders in order to do compute functions enough that eventually there were these standardized compute shaders to make the whole thing legitimized. And so I definitely want to talk about compute shaders, not just the hacked geometry and vertex shader compute operations. There's actually a demo out there that I'll probably show you at some point. You can find it if you want to. It's on the internet, where somebody uses vertex feedback to do a compute operation on an array. Basically, they take an array, load it into memory as a buffer, and then they run a vertex shader to like calculate the squares of everything in the array or something like that. Run it back into the same one with translation feedback, and then read it back into CPU main memory. And I want to show it to you because it's like a super primitive version of what we'll do for the second half of the semester using the GPU for computations. Expressed in basically terms we've already covered. Okay, anyway, that's that. That's the future of the class and whatnot. If you're looking at something to do, if you're feeling weird that there's not enough homework from this class, which might make a certain amount of sense, I just take the demo and make it do something else. Whatever you work on, I'm sure you'll learn something. You decide you want a robot walking through the trees and stomping on them, you will learn something. Do it. Okay, talk to you next time.